In this lesson, we're going to look at more of the characteristics of functions and more of the ways that we can describe functions. And the first thing I want you to do is either use your textbook or a mathematics dictionary and make sure that you understand the definitions to these terms that are on the screen. Okay, so increasing functions, decreasing functions, constant functions, a relative maximum or maxima is the plural, relative minimum or minima is the plural, even functions, odd functions, and piecewise functions. So write down the definitions to those, make sure you understand what it is that's increasing or decreasing, and how to do that. We're going to go through some examples, and you may get a good feel for them from the examples that we do, but I want you to have a formal definition to these terms as well. Here's an example of a function, and when I create these in Excel, I can't put the arrows on them, so I'm going to add the arrows now. So we are seeing that the function goes off to the left on for infinity and on to the right for infinity. And let's describe the domain, the range, the increasing intervals, decreasing intervals, relative minima, relative maxima for this function and for the next one. Okay, so let's start with the domain. We're looking at all the x values, and because the arrows go off to the left and to the right forever, the domain is really going to be negative infinity to infinity. And the range will be the same because the values continue to go up and they continue to go down. So we've got negative infinity to infinity. Now let's look at increasing, where this interval might be or where this function might be increasing. And if we look at the graph, we can see that it's increasing in this value. Remember, we're looking at just the x values for which it's increasing. So it's increasing from x valued 0 to 2. So the interval is the interval 0 to 2 over which it's increasing. If we look at decreasing, and it's important to remember that we're looking at what happens to the function as we go from left to right, so as x increases. So we can see that it's actually decreasing all the way from negative infinity to 0. And it's also decreasing again from 2 to infinity. And then let's look at relative minimum and relative maximum. Okay, and you can see that we've got a low point right here. So it's at 0, 0. And this is an interesting thing with relative minima and maxima, is that there's a couple of ways to talk about them. The relative minimum happens at 0, 0, but we can also say that there's a relative minimum of 0, which is our y value, at 0, which is our x value. And that'll become a little more clearer when we look at the maximum. So we do have a relative maximum as well. Relative. Okay, and there's a maximum over here, and this is the point 2, 4. So the maximum occurs at the point 2, 4. So again, but if we talk about the maximum value, the relative maximum has a value of 4, and it happens at 2. Okay, so the value of the function, think of that as the height of the function. It's the level of it is at 4, and it occurs when x is equal to 2. And let's move on to the next function and do the same um, look at the characteristics of it as well. This is called a sinusoidal function, and we'll spend lots of time with functions that look like this during second semester. And so let's put a closed dot at the end of this graph, at the endpoints here, okay, so that it clearly ends. What's the domain of this function? This might be a good time to pause the video, fill in the domain, the range, relative maxima, relative minima, and increasing and decreasing intervals, okay? So the domain is, remember, is the x coordinates or our independent variable, whatever the horizontal variable is, okay? So the domain is 0 to 540, and because of those dots, we actually need to use square brackets. And our range will be the lowest value is -1 and the highest value is +1, so -1 to +1. So let's look at increasing intervals. So what are the values of x over which the function is increasing as we go left to right? So you can see that we have an increasing section here, and we have another increasing section here. So we can describe those two intervals. One of them is 0 to 90, and one of them is 270 to 450. Okay, and then we can look at our decreasing, and we can see that the function is decreasing here and again here. So we have a decreasing interval from 90 to 270, and we have a decreasing function, or a decreasing interval again from 450 to 540. Notice that we only care about the x values here, okay? We're not concerned with how much it's decreasing by. We just give the interval over which it is decreasing, which is the x values only. Okay, now if we look, we can see that we've got a couple of extrema, or relative minima and maxima, and I'm just going to switch pen colors here if this will let me. Oh, there we go. And so here we've got a relative, no, let's try that once more. Here we've got a relative maximum. No, it just wants to mess with my diagram here, so we'll just stop doing that. I'm going to just press pause here. Okay, I think we got that straightened out. So relative maxima points are right here, and relative minima point is right down there. So we have a relative max. We have two of them. So we have relative maxima of 1, and it's at 2 points. It's at 90 and at 450. And we have a relative minima of -1, and it happens at 270. Okay? Or we could give the coordinates of those 3 points. Okay. Let's move on now to identifying even and odd functions. Okay, and hopefully you've gotten that definition down for doing that. So when you are given a function like example A here, where I have f at x equals 2x cubed minus 5x, the first thing you want to do to determine if the function is even or odd is calculate what happens when you substitute negative x into the function. Okay, so f at negative x, in this case, is going to give me 2 times negative x cubed minus 5 times negative x. Now, negative x cubed is going to be negative still because of that power of 3, so that will give us actually a negative 2x cubed. And negative 5 times negative x gives us a positive 5x. So f at negative x is equal to negative 2x cubed plus 5x. Notice that compared to our original function, the signs on both terms have changed. So it's actually equal to, if you thought of it, it's actually equal to negative the original function, isn't it? 2x cubed minus 5x. I could factor out a negative 1, for instance, okay? So f at negative x is negative the original function. So f at negative x is equal to f at x, and by definition then this is an odd function. So it's odd. Okay, let's look at another example, and we'll do the same method and see what happens. So in example B here, I've got a function g at x. G at x is equal to 2x to the power of 4 minus 6x squared. I'm going to just plug negative x in. And so I'll get 2 times negative x to the power of 4 minus 6 times negative x squared. So when I take negative x and put it to the power of 4, because that's an even power, it's going to end up being positive. So I'll end up with 2x to the power of 4. And the same thing is going to happen here. Negative x times negative x, as I'm squaring that, becomes positive x squared. So we have negative 6 times x squared. So g at negative x is exactly the same as g at x. So g at negative x equals g at x. So this function is even. Okay, so when you plug in negative x into your function and get the same thing as g at x, we have an even function. If the function is exactly the opposite, is the negative of the original function, it's an odd function. So let's look at one more example. Example C here, where we have h at x equals x squared plus 5x minus 3. Let's plug in negative x for that. So h at negative x equals negative x squared plus 5 times negative x minus 3. Well, negative x squared gives me a positive x squared. 5 times negative x gives me a negative 5x minus 3. Okay, so h at negative x is equal to that. Is that the same as h at x? It's not, because this one term has changed, but it's also not the same as negative h at x. So h at negative x does not equal h at x, and h at negative x does not equal negative h at x. So it is neither even nor odd. Okay, so if it's the same after you put the negative in, you have an even function. If it's exactly the opposite sign, it's an odd function. If parts are the same and parts change signs, then it's neither even nor odd. So that's how to find an odd or even function using the equation. Now we're going to use a graph, and it'd be great to do these on a graphing calculator or graphing utility of some sort so that you could see what these look like. I'm going to make a quick sketch of what they look like. So the function f at x, or y equals 2x to the power 4 minus 6x squared, if I were to put that in the graphing calculator, I'm going to get a graph that looks like this. This function is symmetrical about the y-axis. The y-axis here could almost be a mirror, and the line on the left is reflected onto the right. This is an even function. So even functions are symmetrical about the y-axis. And if you think about the earlier definition, it makes sense. When we plug in a negative x for any value, we're going to get the same y value as if we plugged in the positive x value. We've got it symmetrical on both sides of the y-axis. Let's look at an odd function and what their graph looks like. It's a little harder to sketch an odd function for me, but here I've got one, y equals 2x cubed minus 5x. And if I were to sketch that graph, I would end up with a graph that does this on this side and does this on this side. And this is an odd function, and if I were to take it and rotate it right at the center, at the origin here, 0, 0. If I were to rotate this 180 degrees, it would look exactly the same. So odd functions are symmetrical about the origin. And remember, the origin is the point 0, 0. So they rotate 180 degrees to give the same graph. So if you think about what that symmetry means, when we plugged in a negative x value in the earlier example, we got the opposite of what we got with the original x value. So you can see that same thing is happening here. If I choose this point of x and then choose its negative point, I get the opposite y value. On this side it's positive, on this side it's negative. Okay, so that's an odd function. Any graph that does not meet those two requirements, either being even, where it's exactly symmetrical around the y-axis, or that it's exactly rotates around the origin 180 degrees, any function that doesn't meet either one of those comes under the neither category. So as a quick example, if this is my x and y axis and I have a function that looks just like the one we just did, but is symmetrical maybe around this point, this one is neither. Even though it has the same shape, because it isn't centered at the origin, it falls under that neither category. Okay, and the last thing that we're going to look at in this lesson is our difference quotient formula. And what it does is it gives you what the rate of change for a function is over an interval. So I can see that I've made a mistake here in typing it out. It's f at x plus h minus f at x. So this should say in the brackets here x plus h. So f at x plus h minus f at x all over h, where h does not equal 0 because, of course, remember, we can't divide by 0 because then we are undefined. Okay, so if you think of a graph of some shape, and we'll just do something like this curve here. If you think of this value as being f at x, okay, and so here's my x, and this will be my x plus h. So I've moved over an interval of h units, okay? So I've gone from x to x plus h. So here's the value of the function at x plus h. So what I'm doing is I'm subtracting the f at x value from the f at x plus h value, which in this case is positive because the x plus h is higher, and then I divide it by the distance of the interval, okay? Which is going to be very familiar to some of you. So let's take a look at this example of f at x equals 3x squared plus 2x minus 6. And I'm just going to scroll a little bit here to give us a little bit more space. Let's first just calculate what f at x plus h is. So f at x plus h will be 3 times x plus h squared plus 2 times x plus h minus 6. Okay, so sorry about that. So we're just substituting x plus h in wherever there's an x in the original function. Now we will expand through those brackets and simplify. So that's 3 times, if you think about what x plus h times x plus h is, remembering that x plus h squared is equal to x plus h times x plus h. Okay, and we need to multiply through all those brackets. Okay, we end up with x squared plus 2xh plus h squared. Okay, plus 2x plus 2h minus 6. Because I'm multiplying through these brackets as well. Okay, so let's multiply through all those brackets here. So I've got 3x squared plus 6xh plus 3h squared plus 2x plus 2h minus 6, which looks like a really nasty mess. Okay, but now to finish this off, I need to subtract. Okay, so I'm taking the f at x plus h, and I'm going to subtract the f at x and put it all over h. Let me just make a little sketch here just to separate that from the thinking work there. So f at x plus h minus f at x all over h is going to be equal to, so there's my f at x plus h, 3x squared plus 6xh plus 3h squared plus 2x plus 2h minus 6. And I'm subtracting f at x. So my original f at x is 3x squared plus 2x minus 6. And the whole thing over h. So we need to be very careful as we collect our like terms here, okay? So notice that I have a 3x squared and I'm subtracting a 3x squared. I've got a 2x and I'm subtracting a 2x. I've got a negative 6 and I'm subtracting a negative 6. Okay, so I'm left with 6xh plus 3h squared plus 2h all over h. So let's factor an h out of the numerator there because I see that as a common factor I've got an h in all of those terms. So that's h times 6x plus 3h plus 2 all over h. So now I can go h divided by h, and I'm left with 6x plus 3h plus 2. And that is my difference quotient, okay? Difference quotient. They usually will simplify to something much simpler than it seems like it's going to be from our middle step there. Okay, and that's it for today's lesson.